Hey everyone, welcome back. In our previous video, we learned how to find eigenvalues and eigenvectors for 3x3 matrices with distinct eigenvalues. Today, we are tackling a slightly trickier scenario, repeated eigenvalues. This can introduce some interesting challenges, but let's break it as we have done it earlier for a 2x2 matrix. I have added the video here. Just a quick reminder, eigenvalues are the scalar values lambda that satisfy the equation AV is equal to lambda times V, where A is our matrix and V is the eigenvector. We find eigenvalues by solving the characteristic equation which is given by determinant of A minus lambda I is equal to 0. When we calculate the characteristic polynomial of a 3x3 matrix, we might encounter cases where the polynomial has repeated roots. This means we have repeated eigenvalues. Let's see how this affects finding the eigenvectors. Consider the given matrix. For this, we will form the matrix A minus lambda I, which is equal to 2 minus lambda 1, 0, 0, 2 minus lambda 0, 0, 0 and 1 minus lambda. Now the characteristic equation is given by the determinant of this equal to 0, that is A minus lambda times I is equal to 0, which gives us the determinant of 2 minus lambda 1, 0, 0, 2 minus lambda 0, 0, 0, 1 minus lambda is equal to 0. Solving this gives us 2 minus lambda multiplied by the determinant of this minor matrix, which is 2 minus lambda times 1 minus lambda minus 0, and then we have minus 1 times the corresponding minor, which is 0 plus 0 is equal to 0. Simplifying, we get 2 minus lambda, 2 minus lambda, 1 minus lambda is equal to 0, and this gives us lambda is equal to 2, 2 and 1. It can be seen that A has 2 as a repeated eigenvalue and the other eigenvalue is 1. Now next we are going to find out the eigenvector corresponding to lambda equal to 2. For that, we start with the equation A minus lambda times I into V is equal to 0, which gives us A minus 2 times of I into V is equal to 0. Now substituting lambda equal to 2 in this expression, we get 0, 1, 0, 0, 0, 0 and 0, 0, negative 1 times V, which will be x1, x2, x3 is equal to 0, 0, 0. Simplifying this as an equation, we get x2 is equal to 0 from the first row. From the second row, we get 0 is equal to 0, and from the third row, we get minus x3 is equal to 0, which implies that we have x2 equal to x3 is equal to 0 and x1 is a free variable. So therefore the eigenvector corresponding to lambda equal to 2 is given by v1 equal to x1 0 0, where x1 is a real number. If you put x1 as 1, we get v1 is equal to 1 0 0. Since the eigenvector contains only one free variable, we cannot find any other linearly independent eigenvector for this particular eigenvalue lambda equal to 2. Now let's calculate the eigenvalue for lambda equal to 1. So the equation reduces to A minus 1 times I into V is equal to 0, which will give us 2 minus 1, that is 1, 1, 0, 0, again 2 minus 1, which is 1, 0, 0, 0 and 1 minus 1, which is 0 times V, which is x1, x2, x3 is equal to 0, 0, 0. This gives us x1 plus x2 is equal to 0, x2 is equal to 0 and 0 is equal to 0. From the second equation, we have x2 is equal to 0, and if we substitute x2 equal to 0 in the first equation, then we get x1 is also equal to 0. Thus we have x1 equal to x2 is equal to 0, and again x3 is a free variable, so therefore the eigenvector corresponding to lambda equal to 1 is given by 0, 0, x3, where x3 is a real number. If we put x3 as 1, we get v2 as 0, 0, 1. Again, since there is only one free variable, we will have only one linearly independent eigenvector. We cannot find another one. As you can see, when we have repeated eigenvalues, we might not always find as many linearly independent eigenvectors as the order of the matrix. In this example, we only found one linearly independent eigenvector for the repeated eigenvalue lambda equal to 2. This means that the matrix A is defective. Handling repeated eigenvalues in 3x3 matrices requires careful attention. Remember that the number of linearly independent vectors might be less than the matrix order, indicating a defective matrix. Practice with different examples to solidify your understanding. If you found this video helpful, please give it a thumbs up and subscribe for more linear algebra tutorials. Let me know in the comments if you have any questions or suggestions for future videos. Thanks for watching and happy learning.